Yeah, so today's lecture we will continue on Laplace transformation. So today is Friday, 23rd. The readings are page 98 to 99. And also it's the due date for homework 6. I expect everyone submit homework 6. Then next week, 26 on Monday, the readings are page 99 to 104. Then in Wednesday, 28, this will be our readings page 104 to 106, and also it's the due date for homework number 7. And you can go to Canvas and see what's the requirement for homework number 7. And that Wednesday will be the last meeting before the spring break. Then you can enjoy the spring break, start on Wednesday. So Friday, there will be no class. Okay. Then we have some important tables. Again, those Laplace transformation tables, which is table 3.1 about transformation, 3.2 about the properties, this importance and how to apply this. So most likely, whenever in the test, this table will be provided to you. Or, I'm not sure, or you need to have them with you. So, whatever, you don't need to memorize them, but you need to know how to use them. So, like, these are tools that you need to know how to use them. Those, again, those are page 96 and 97. Okay, let's start some theorems. And these theorems basically, we would like to use Laplace transformation that help us in calculating something or doing some analysis. So basically, let's take the benefits or the advantages of Laplace transformation in our analysis. So the first thing that I would like to discuss today, initial value theorem. So basically, if you need to discuss or if you need to calculate initial value of any function, basically, in time domain, how do we calculate the initial value? You will find the limits when t equal to 0. So basically, it's the limits of x of t when t equal to 0, goes to 0. Then you can apply the limits theorem. That's using time domain. While in frequency domain, or in other words, in Laplace domain, we will convert x of t to be x of s. Then how to find the initial value? Basically, x of 0, and I'll say like 0 from right, it will be the limits s, x of s, such that s goes to infinity. Okay? So the first thing that we realize is s times x of s. The second thing, the limit when s goes to 0, goes to infinity. Why when s goes to infinity, not 0? Most likely the frequency is the opposite of the time, right? F equal 1 over t, something like that. Something that how you can imagine it. Then 1 over 0, infinity. So basically, whenever he said like initial value, we will go when s goes to infinity because 1 over 0 will be infinity. Because the frequencies they are 1 over the time. Something like that. Then that's how we will use, this is called initial value theorem. Initial value theorem, IVT. This has many applications that you will see it later in other courses, different courses. Electrical engineering, you will see this problem or this theorem is very important in our analysis. Then sometimes when you have the problem or the system written in frequency domain, you don't need to convert it back to time domain and calculate the initial value. You can calculate it basically direct using initial value theorem, IVT. Then the second theorem is called final value theorem. So in time domain, we used to do it when we make the limits goes to infinity. In time domain, we used to say the final value x of infinity equals to the limits when t goes to infinity x of t. That's what we used to do. But here, using Laplace domain or frequency domain, x of infinity will be the limits when s goes to 0, s x of s. So it will be just when s goes to 0 and s goes to infinity, because 1 over infinity, as we know, it is 0, right? Then that's how we calculate it. And this is called final value theorem, like FVT, IVT and IVT. But actually, final value theorem is not true every time. It's not always true. That's a concern. It's not always true. How can we know if this is true or not? Basically, we will say this much. If s, x of s, has poles on the imaginary axis, that's one step. Or if s of x of s has poles on right half plane, then any of those, what will happen? X of infinity does not exist. What do I mean by right half plane or imaginary axis? So this is the x-plane root, xy, the xy plane. Then basically this is the imaginary axis, this is the real axis. So basically, we will say that the poles area must be in the left half plane. LHP, left half plane, and this RHP, right half plane. So we need our targets is to be here, not to be outside. That's the overall thoughts, that to make sure everything in the right half plane. While right half plane is not correct, and the overall imaginary axis, which is this imaginary axis, is not correct. We don't want to avoid these two areas. But keep in mind, it must be s times x of s, not x of s alone, not x of s. Okay? Our target is to study s, x of s. So don't forget to multiply by s. Then you need to think about it. Okay, so how can we figure out, or what's the point of using this? Let's see an example. Example, we have x of s equals 1 over s minus 1. Okay? Now we will say s, x of s will be s over s minus 1. Is this correct? Yes, that's correct. Then look at the poles related to the roots of the denominator. So here, s minus 1 equals 0, therefore s equal 1. So s equal 1, this is positive, or this is most likely on right half plane. So basically, if I make the plots, you will see the location of the pole will be here actually. It's not on the left half, which is final value theorem will not be correct. So we will say, since s, x of s is on right half plane, therefore final value theorem is not correct. We cannot apply it. Okay, how can I validate this? Validate this. So basically, we have x of s as 1s minus 1, right? Convert this to time. So you will have x of t equals e power t u of t, e power positive t, because here s equal 1, therefore power will be 1. Okay? So e power at. Now let's find the limits. X of infinity equals to limits x of t when t goes to infinity, which is, will be e power infinity. E power infinity is what? Infinity, right? Now, let's try to apply the S, or limits actually, final value theorem, to see will we get the same answer or not. Final value theorem, limits when S goes to 0, S x of S, this will be as S, limits S over S minus 1 when S goes to S goes to 0, which will be 0, this will be 0 over 0 minus 1, so the answer will be 0. Then we realize that final value theorem says it is 0, but time domain says it is infinity, which is contradicts. So which one is correct? The time domain is correct. The final value theorem is not. So always, every time, trust the time domain. So that's one approach that says the final value theorem is not correct. And again, it can be not correct if we have poles on the right half plane or in the imaginary axis. But again, when you test only S x of S. Let's do another thing, another example. Like we have 1 over S plus 1. And we need to find the final value theorem. Apply the final value theorem. So basically, this is x of S. What we will say S x of S equals to S over S plus 1. The poles here, S equal negative 1. This is a left half plane. So final value theorem will be correct. So basically, S equal negative 1 will be taken. So how can we validate or make sure that we can get the final value theorem? So final value theorem says S, or the limits, S x of S when S goes to 0, which is going to be as S over S plus 1, which will be 0 over 0 plus 1, then it will be 0. Okay? Let's validate this using time domain. Time domain, we will make it as find x of S. X of S actually is 1 over S plus 1. So this means S plus 1 equal to negative 1. Then to convert this to time domain, it will be as x of t will be e power negative t u of t. Then in time domain, to find the limits when t goes to infinity, or x of t, which is e power negative infinity, e power negative infinity equals to 0. Therefore, it's correct. So final value theorem, the same as time domain. Okay? You don't need to find every time to make this comparison, time domain and final value theorem. But here, I'm just for demonstration, I'm showing you that here, the final value theorem is working well, without any problems. Okay? One more example. We have x of S equal to 1 over S times S plus 1. If we look at x of S alone, you will see there is a pole at negative 1, pole at 0. Since there's a pole at 0, this will clear the problem according to final value theorem. I don't think so. Why? Because our targets say S x of S. It will be S over S times S plus 1. S and S cancel each other. So it will be 1 over S plus 1. So when we do it in the xy plane mode, you will realize we have only a pole at negative 1. Because again, remember, we are studying only S of x of S. We are not studying x of S alone. So therefore, the final value theorem exists. okay? And it will work fine. Okay, does this make sense? So whenever you test S x of S. Don't test x of S alone. And here's one example that if you did test x of S, it will be different than when you test S of x of S. So basically, final value theorem, x of infinity will be the limit when S goes to 0, S x of S, which will be 1 over S plus 1, which is 1 over 0 plus 1. So the final answer will be. Okay? Is this clear? So you need just to be aware that whenever we need to test the final value theorem, is it working or not, keep in mind S times x of S. Okay, let's do another example. Let's assume that we have x of t equal to cosine omega t times u of t. According to the Laplace transformation, x of S will be S over S squared plus omega squared. Then if we need to find the poles for Sx of S, it will be as S squared over S squared plus omega squared. If we need to find the pole, it will be S squared over S plus j omega, S minus j. So by looking at the xy plane below, you will see a pole at j omega. My main target is to look for the poles like this. You're looking at the pole at omega j omega. So you will see these two are located on where? On the imaginary axis. So once these are located in the imaginary axis, this means final value theorem will not be applied. Cannot be applied. Because they are not on the left half plane. We need to be exactly on the left half plane. While if they are at the imaginary axis, it will not work. So let's assume whatever. Let's assume that we need to calculate. Let's try to apply. So the limits S goes to 0, Sx of S means that S squared over S squared plus omega squared, make it 0, which will make it 0 over 0 plus omega squared, then it will be 0. So the final answer is written as 0. The final value is, using the final value theorem, is 0. But again, it's not applied, it's not correct. But actually, if we do it in time domain, limit when t goes to infinity for x of t, which is limits when t goes to infinity for sine or cosine, which is we have here cosine omega t times u of t. Okay? What's the limits of the cosine when t goes to 0? Goes to infinity. You know? Look at the waveform, agent positive waveform. So the cosine is something like this. What's the value when it goes to infinity? We don't know, right? It's because it's keep periodic, keep repeating itself. It will not decay or going up. It's not like exponential going up to the infinity or go to down infinity. Then it's not working at all. I mean, we cannot find it. So as a result, we will say x of infinity does not exist. Okay? Does not exist because we don't know it when it goes down. So as a result, we will say that we can summarize some points. That final value theorem exists or true if all of S, x of S, are on left half plane. Okay? Then this other thing, which is if poles are on right half plane, then I will say final value theorem cannot work, or does not work. So what we will do, use time domain. Okay? Now, other thing, which is if poles are on imaginary axis only. Imaginary axis. In this situation, what we will say, yes, final value theorem cannot work, or does it work? But there is also something that we will say that x of infinity is over all cannot be computed, or does not exist. Okay? There will not be any value. Okay? Most likely, this happens for the periodic signals. Periodic signals, where the signal that there's a repetitive waveform every certain period of time, all of these periodic signals, they don't have a value, just call it an infinite value, or I'm sorry, final value, or final value. There's no final value. Okay? Let's do an example. X of s equal to 2 over s plus 2, s plus 4. Let me before that actually. Sorry, let me do that example with the and I have x of t actually equals to r of t. Then x of s will be 1 over s squared. Okay? So the time domain, or let me say like apply the final value theorem, look at the poles, x of s equal to what? S over s squared, therefore the answer will be 1 over s, right? So the poles located at the origin. When you plot the node, it's at the origin, which is here. It's at the origin, but still on the imaginary axis, gy plane. Therefore, final value theorem cannot be applied. Final value theorem is wrong. How can I validate the answer? Basically, try to apply the final value theorem, which is limits s x of s when s goes to 0, which will be s over s squared, then it will be 1 over s, 1 over 0 equal to infinity. Then here, what we will say is time domain x of infinity equal limits when t goes to infinity, r of t. R of t basically is a function with time goes to the infinity, therefore it will be infinity. So even though both answers goes to the infinity, but the overall imagine about the x or this problem, it shouldn't, final value theorem, it shouldn't be applied here. Even though, I mean, yeah, we realize this is infinity, yes. But in general, whenever you see something like this, the final value theorem will not be applied. So what's happening on the final value theorem, which is when it is located at 0, then it will be like goes to be something called unstable. Something like the stability that we will learn later in the control system. Anyway, let's go to another example. Okay, this example, which is assume we have x of s equal to 2 over s plus 2, s plus 4. And we need to calculate the following. A, which is plugs, poles, and zeros. B, we need to find x of 0 positive. C, we need to find x of infinity. That's our target. How to solve it? Let's start with number 1, with number A, which is poles and zeros. This is again x of s, which is 2 over s, s plus 2, s plus 4. Is there any zeros for the numerator? No, no zeros. So zeros, not applicable. Poles, what are the roots of the denominator? Basically, s equals 0, look at this term, s plus 2, s plus 4, make it equal 0. So we have s equals 0, s equal negative 2, s equal negative 4. Is this correct? That's all good. So basically, poles located at s equals 0, negative 2, negative 4, then we will plot. Because we need to plot them. There is 1 at 0, 1 at negative 2, 1 at negative 4. Okay? Then problem A is done. Problem B, we need to find x of 0. X of 0, or sometimes we write x of 0 from right. Even if we write as x of 0 alone, it can be okay. But scientifically, we write the x of 0 from right. How to find this? Now the question is, can we apply final value theorem? We say no, because we have 1 pole and 0, right? That's what it looks like. But let's go back to the final value theorem and we just want to focus on that. Study s x of s, not x of s. Here, x of s has a 0. Let's study s of x of s. X of s equals to be 2s over s plus 2, s plus 4. S and s cancel each other. That's it. So it will be 2 over s plus 2, s plus 4. Then if we plug them, it will be here at negative 2, negative 4, then there is nothing at the origin. So we can apply final value. So we can say that x of 0 positive equals limits using initial. We can apply final value, and initial value theorem should work without any problem. Let's see because of the limits when s goes to 0 as x of s, which is going to be as 2s over s plus 2, s plus 4, so s and s cancel each other. Then it will be, before I do the limits, so it will be 2 over 0 plus 2 times 0 plus 4, so 2 times 4, 8, 2 over 8, 2 over 8, then it will be 1 over 4. That's x of infinity. Okay? So final value theorem can be applied without any problem. How about initial value theorem, which is part B, to calculate x of 0 positive. X of 0 positive using initial value theorem equals to limits when s goes to infinity, s x of s, so which is going to be as 2 s over s, s plus 2 for the group. So limits s goes to infinity, 2s over s, s plus 2, s plus 4, s and s cancel each other. Then it will be as limits when s goes to infinity, 2 over s plus 2, s plus 4, substitute s as infinity, so it will be 2 over infinity plus 2, infinity plus 4, so infinity plus infinity, which will make it plus 2, infinity times infinity, infinity, so it will be 2 over infinity, then the answer is 0. Okay? Then problem 1. Any questions? to example, just like this is our Laplace transform. Different values. Assume we have this graph t x of t t uppercase, t uppercase, t 0. And we need to calculate Laplace transform. Find x of s. In order to do, again, I mentioned this before, and also when you have a plot and you need to calculate Laplace transformation, find the time period and find the equations and do it for the equations. Then do it for the plot. Okay? The equations will make it much easier. So x of t. X of t equal to what? This is written as round function, right? So you can either write it as tu of t or you can write it as r of t. So we can say between 0 to t, it is as r of t. Because the slope is 1, so r of t. Then minus, then between t until 2t, it is like r of t minus t uppercase. But this t is going to go from slope 1 to be negative 1. Therefore, it will be negative 1 and another negative 1. Therefore, it will be minus 2. R of t minus 2. Why negative 2, not negative 1? Because the slope was 1. If you put negative 1 alone, the slope will be 0. But our target is to make the slope negative 1, so it will be from 1. Then subtract 0, subtract 1, negative 2. So it will be the overall subtraction is 2. Then at 2t, what will happen? We need to cancel the effect of r of t. So we will make it positive with the slope positive, r of t minus 2. So the third thing, which is to cancel the effect, and the overall will be 0. This is x of t. Now, how to do the Laplace transformation? Laplace transformation of x of t will be, you can distribute the Laplace transformation, which is distributive, Laplace of r of t minus 2, Laplace of r of t minus t uppercase, plus Laplace of r of t minus 2. Now, how to find this? Laplace transformation according to the table that we have, 1 over s squared minus 2. Laplace transformation of this one, it's actually as r of t and shift with t, with t minus tau, which means t equal t upper. So, what will happen? It will be as the first thing, r of t 1 over s squared times the shifts e power negative s, and it is t. Once here, the shift is t. Okay, let me write this. I'm just moving it down. So, then, plus, this is r of t and shift by t equal to 2t. So it's going to be as plus 1 over s squared e power negative 2st. Okay? That's it. You can simplify it as 1 over s squared minus 2 e power negative st. And you can say actually all of the squared plus e power negative 2st. This is x plus equals to 10. But now let's go to another property, then we'll go to the convolution. There's a property that's called frequency differentiation. I'm not going to go through the derivation, but I just want you to let you know when there is t times x of t, you can see it in the table, table 3.2. it will be the negative d by ds of x of s. So the effect of t will make the derivative. When a function multiplied by t, t will make it the negative derivative. How about frequency integration? Basically, we have 1 over t x of t. So this will be as integral from s to infinity x of s ds. But in order to distinguish between this s and this s, I will add it as s1 or s1. So that's s1 is called as a dummy variable, just to distinguish between s and integral and s and s. So basically, if it is 1 over t, this will make integral. If there's t, this will make this will make derivative. In other words, we can say if it is 1 over t, it's equal to t inverse, such that this will make the derivative. Derivative inverse minus 1 is integral. Okay, like the order of derivative. How about if there's t squared, t cubic, then basically if we have higher derivative, this will make it, or t squared, t third, etc. This will make second order derivative, third order derivative. So you will make first, whenever we have, for example, t squared x of t. So what you will make it as t times t x of t. So you will do the first thing, the Laplace transformation of this, which will be negative d by ds x of s. Then you still need to do the Laplace transformation of t with this function. So then another t, it will be negative d by ds, negative d by ds x of s. So negative and negative will cancel each other. So which will make it as d squared, and we'll make it positive here, then d squared over ds squared x of s, which will be second order. So every derivative, there will be negative sign. Okay? Then the same thing for the integral. If you have 1 over t squared, then there will be double integral. Or if there is 1 over t cubic triple integral, and the same thing for higher orders. This is, by the way, the tables. This table 3.1, 3.2. So here just for your information, that's when we have t, x of t, 1 over t. That's how we do. This way, this is the final value theorem, the initial value theorem. Then the last thing, which is the convolution. This is the last property. The convolution. Okay, and this is, by the way, the tables. Those are the tables. Even when we have higher order with something, we need to know how to use all of these two tables. Table 3.2, 3.1 are very important. Now, let's discuss the convolution, which is the last property. Convolution. In time domain, we didn't like a convolution, right? Because it's kind of heavy to make that, entering the area, leaving the area. And with small systems, it was very hard. How about if the system is complicated with sine, cosine, with large big systems, or in real life systems, which will make it very complicated to do the convolution. Therefore, we said, like, here is the advantage of the Laplace transformation. So when there is a convolution, it will be converted to be products. So this happens if x of t, x1 of t, and x2 of t are causal, then x1 of t convolve with x2 of t. When we do the Laplace transformation, it will be x1 of s times x2 of s. It will be products. So convolution, time domain, will be products, frequency, which is something great, which is something super great. So basically, whenever we deal with the convolution, we don't need to do all of these trouble, all of these mistakes, all of these problems. So basically, if we need to do, for example, convolution, u of t times, I would say like r of t, I'm sorry. We need to do a convolution like x1 as u of t, x2 as r of t. Then we do the convolution u of t convolved with r of t. The best way is to convert u of t to be 1 over s. This is x1 of s. x2 of s will be 1 over s cubic. Okay? Then the convolution will be x1 of s times x2 of s, which will be 1 over s times 1 over s squared, then it will be 1 over s cubic. After that, we can do Laplace inverse. So the overall procedure, starting from the procedure, solving or compute convolution by Laplace transformation. The procedure, the first thing, convert x1 and x2 from time domain to Laplace. Then compute the product. Which is x1 of s times x2 of s. This is equal, for example, y of s. Then the last thing, which is convert x of s, y of s, which is the output, from Laplace domain to time domain. Which is something we call a Laplace inverse. Then, we know how to do Laplace, we know how to do that. So, the convolution now is easy. It's no longer difficult like what we did before. But the thing is, in the trick, how to do Laplace transform inverse. So let me give you, I'll start with one example about circuits analysis. Then we will see how we can solve the circuit analysis using the transient or using Laplace inverse. Are you familiar with RLC transients, second order? Did you take this from the circuit class?
I think only first one.
Only first.
We focus on first one.
In first one. Okay.
We
Now,
might have like thrown a problem at one lecture, but we never really did it.
one lecture problem. Should be fine. That's why we here. Then let's discuss RLC, second order class, RLC transients. Let's go back to circuits. RLC. So basically, RLC transients, we will have second order differential equation. Second order ordinary differential equation. Basically, how we know it's second order, we have inductor, we have capacitor. So we have two storage elements. Therefore, second order. Okay. How can we do this? How can we solve this? We will use Laplace transformation. So I'm going to shortcut as LP, Laplace transform. Let me draw the circuit. Let me assume a DC. So I'm going to go more complicated. So I'm going to assume it has, this is VO, and the voltage is this DC source 1.6 volts. Then there is a switch that closed at t equals 0. Then we have a resistor R. We have a capacitor C. then we have an inductor L. The resistor, we can write the values, different colors. So we have 1.6 volt, the inductor 0.4 Henry, capacitor 0.1 Farad, and resistor 4 ohms. And we need to have some initial values. Let's assume the initial value, most likely for the capacitor voltage, equal to 0.4 volts. Let's assume the initial value of the inductor currents equal to 0. Okay? Because according to our RLC transient circuits, you need to know the initial values for them, or we need to calculate them before the switch and after the switch. But I'm going to just assume it like this. Okay? Then how to solve these circuits? The first thing, let's try to make this circuit something similar to signals. We can, the inductor, we can say that the current of the inductor L di by dt. For the capacitor, the voltage equals C dV by dt, di by dt. Di by dt, something like that. That's what we know about this. But let's think about the switch. That's one of the things that we have. In order to make it to apply Laplace transformation, we have a switch. The switch open at t equals 0. Before t equals 0, it will be 0, right? So the switch looks like what? Something opens at t equals 0. One of the functions that we learned, does it look like impulse, delta, Q of t, U of t? Correct. So I will say, that's one thing interesting, the voltage source and U and the switch can work as a single source, plus minus, VO times U of t, which is in other words, 1.6 times U of t. Then, the remaining elements are going to keep them right. Resistor, capacitor, right? Now here, in the circuit analysis, we cannot model the switch. We said nonlinear elements, right? But here now we can model it a little bit. Here is, let's take the advantages of the signals and systems in our logical circuit analysis. So, how to find this? So basically, the resistor again, it is 4 ohms. Capacitor, 1 Farad. The initial value of DC of 0 equal to 0.4 volts. That's given. And I of the inductor equal to 0. And the inductor is 0.4 here. Now, how can I solve this? Let's assume our target is to calculate I of t. Let me write here. Find I of t. How to find I of t? Basically, the current. This is I of t. We need to calculate I of t. How to deal with this? KVL, right? Listen, KVL, start from the left bottom corner, then travel clockwise, and I'm going to put a voltage, assign a voltage polarity for everything. So this is VO, not IO, which is basically I can call this as VS of t. And this is plus minus VR of t, plus minus VC of t, plus minus VL of t. Okay? So I'm letting like the current enters the positive, so I can guarantee that Ohm's law is positive or the other formulas are positive. So that's our standard. So when we do KVL, start from the left bottom corner, then travel clockwise. Negative Vs of t plus Vr of t plus Vc of t plus Vl of t equals to 0. Let's put them in the other side and make Vs of t from one side. So this is Vs of t equals Vr of t plus Vc of t plus Vl of t. Now let's substitute. Vs of t we have this equation. Vr of t Ohm's law. Vc I, which is 1 over c, the integral of the currents, while Vl equal L di by dt, which is basically, we will form the differential equation. So before, now we don't have time. we will continue this next lecture, which is we will start from VSFT and see how we can solve this. So see you on